Welcome back. In this session, we discuss rings of polynomials. In mathematics, especially in the field of abstract algebra, a polynomial ring is a ring formed from the set of polynomials in one or more variables with coefficients in another ring. In this session, we consider rings of polynomials and we will see that under some conditions, such rings are integral domains. We will see that there is no field of polynomials. However, field of quotients can be formed from an integral domain of polynomials. Rings of polynomials. Definition: polynomial with a coefficient in a ring. Let R be a ring. A polynomial f of x with the coefficients in the ring R is an infinite formal sum sigma I equal to 0 to infinity ai x raised to I, which is equal to a naught plus a1x plus etc. an x raised to n plus etc., where a belongs to R and a is equal to 0 for all but a finite number of values of I. Here the polynomial is in the indeterminate x. The ai are coefficients of f of x. If for some I greater than or equal to 0, it is true that a not equal to 0. The largest such a value of I is the degree of f of x. If all ai equal to 0, the polynomial is called 0 polynomial, and in that case the degree of the polynomial is undefined. A polynomial of degree 0 is a constant. That is, if f of x is a polynomial of degree 0 with coefficients from the ring R, then f of x equal to a naught for some a naught belongs to R. Hence, we can regard an element in a ring R as a constant polynomial. Two polynomials are considered to be equal if and only if the corresponding coefficients for each power of x are equal. The set of all polynomials in an indeterminate x with coefficients in a ring R is denoted by R of x. We first show that R of x is a ring under the two binary operations, viz. The polynomial addition and multiplication defined below. If f of x equal to a naught plus a1x plus etc. an x raised to n plus etc. and g of x equal to b naught plus b1x plus etc. bn x raised to n plus etc. are elements in R of x, then polynomial addition f plus g is given in terms of its values at the points x, that is by f plus g of x, and it is given by f plus g of x equal to f of x plus g of x, which is equal to c naught plus c1x plus etc. cn x raised to n plus etc. Equation 1, where cn is equal to an plus bn, and for polynomial multiplication f into g, we have f into g of x is equal to f of x into g of x, which is equal to d naught plus d1x plus etc. dn x raised to n plus etc. Equation 2, where dn is equal to sigma I equal to 0 to n ai bn minus I. Observe that both ci and di are 0 for all but a finite number of values of I. So, the definitions given in 1 and 2 make both f plus g and f into g polynomials. Hence, the binary operations are well defined. The polynomial addition in 1 and multiplication in 2 are sometimes called pointwise addition and pointwise multiplication of polynomials respectively. Theorem 1. The set R of x of all polynomials in an indeterminate x with coefficients in a ring R is a ring under the polynomial addition and multiplication. If R is commutative, so is R of x, and if R has unity 1, then 1 is also unity for R of x. Proof. By the discussion just above, R of x is closed under the operations polynomial addition and polynomial multiplication. It can be verified that if f of x, g of x, h of x belongs to R of x, then f of x plus g of x plus h of x equal to f of x plus g of x plus h of x. This proves the associativity of polynomial addition. The 0 polynomial is the additive identity. For any polynomial f of x equal to a naught plus a1x plus etc. an x raised to n plus etc. belongs to R of x, minus f of x equal to minus a naught minus a1x minus etc. minus an x raised to n minus etc. also belongs to R of x and is the additive inverse of f of x. By the commutativity of addition in the ring R, it can be easily seen that polynomial addition R of x is commutative. Hence, R of x is an abelian group under addition. We prove the associative law using the rings axioms of the ring R. Sigma I equal to 0 to infinity ai x raised to I into sigma j is equal to 0 to infinity bj x raised to j into sigma k is equal to 0 to infinity ck x raised to k equal to sigma n equal to 0 to infinity into sigma I is equal to 0 to n ai b n minus I x raised to n into sigma k is equal to 0 to infinity ck x raised to k by the definition of polynomial multiplication, which is equal to sigma s equal to 0 to infinity sigma n equal to 0 to s sigma I is equal to 0 to n ai b n minus I into c s minus n into x raised to s by the definition of polynomial addition, which is equal to sigma s is equal to 0 to infinity into sigma I plus j plus k equal to s ai bj ck into x raised to s, which is equal to sigma s is equal to 0 to infinity sigma m is equal to 0 to s a s minus m into sigma j is equal to 0 to m bj c m minus j whole into x raised to s, which is equal to sigma I is equal to 0 to infinity ai x raised to I into sigma m is equal to 0 to infinity sigma j is equal to 0 to m bj c m minus j into x raised to m, which is equal to sigma I is equal to 0 to infinity ai x raised to I into sigma j is equal to 0 to infinity bj x raised to j into sigma k is equal to 0 to infinity ck x raised to k. The distributive laws can be proved similarly. If R is commutative, then sigma I is equal to 0 to n ai bn minus I equal to sigma I is equal to 0 to n bi a n minus I, so that R of x is also a commutative ring. If R has a unity 1, then the same is a unity in R of x. Remark: sigma I is equal to 0 to n ai bn minus I need not equal to sigma I is equal to 0 to n bi a n minus I if R is not commutative. Hence, in this case the ring R of x is not commutative. Example 1. Recall that set 2 is equal to set of all 0 1 is a ring under addition modulo 2 and multiplication modulo 2. Hence, by theorem 1, set 2x is the ring of all polynomials in the indeterminate x with coefficients in the ring set 2. For the polynomial x plus 1 in set 2x, we have x plus 1 whole square is equal to x plus 1 into x plus 1, which is equal to x square plus 1 plus 1 into x plus 1, which is equal to x square plus 0 into x plus 1, which is equal to x square plus 1, and x plus 1 plus x plus 1 is equal to 1 plus 1 into x plus 1 plus 1, which is equal to 0 into x plus 0, which is equal to 0. Remarks: if R is a ring, R of x is also a ring. R of x into y is the set of all polynomials in the indeterminate y with the coefficients in the ring R of x. Hence, by theorem 1, R of x of y is also a ring. It can be observed that R of x of y actually is the set of all polynomials in the indeterminates x and y with the coefficients in the ring R. R of x y is the set of all polynomials in the indeterminates x and y with the coefficients in the ring R. R of y of x is the set of all polynomials in the indeterminate x with the coefficients in the ring R of y. It can be seen that R of x of y is equal to R of y of x, which is equal to R of x y. R of x1 comma etc. xn is the ring of polynomials in the n indeterminates xi with the coefficients in R. Integral domain of polynomials. Theorem 2. If D is an integral domain, the ring D of x is also an integral domain. Proof. Being an integral domain, D is a commutative ring with unity. Hence, by theorem 1, D of x is a commutative ring with unity. It remains to show that D of x contains no divisors of 0. Before proving this, we observe that one of the properties of the polynomial multiplication, which says that product of two non-zero polynomials is also a non-zero polynomial. Indeed, if f is a polynomial of degree m with the coefficient of x raised to m is am not equal to 0 and g is a polynomial of degree n with the coefficient of x raised to n is bn not equal to 0, then their product is the polynomial f into g of degree m plus n with the coefficient of x raised to m plus n is am into bn not equal to 0. Here we have used the fact that D is an integral domain and hence the product of non-zero elements of am and bn is also non-zero. The above observation can be used to show that there are no divisors of 0 in D of x. Suppose f is a polynomial of degree m with the coefficient of x raised to m is am not equal to 0 and the product f into g equal to 0, the 0 polynomial. We have to show that g is the 0 polynomial. If g is not the 0 polynomial, it has degree say n. If the coefficient of x raised to n is bn, then bn not equal to 0. Then f into g is of degree with the coefficient of x raised to m plus n is am into bn not equal to 0. This is impossible since f into g is the 0 polynomial. This contradiction allows us to conclude that D of x contains no divisors of 0. This completes the proof of the theorem. Since every field is an integral domain, the following result follows immediately from the theorem. Corollary: if F is a field, the ring f of x is an integral domain. Remark: f of x is not a field, for in particular the polynomial x has no multiplicative inverse in f of x. The possible multiplicative inverse of x is x raised to minus 1, which has negative exponent and hence not a polynomial. Construction of field of quotients f of x from the integral domain f of x. Since f of x is an integral domain, it is possible to construct the field of quotients f of x of f of x. Any element of f of x can be expressed as a quotient f of x by g of x of two polynomials f of x and g of x in f of x with g of x not equal to 0. Notation: the field of rational functions in n indeterminates xi over f is denoted by f of x1, etc. xn. The evaluation homomorphism. Theorem 3. The evaluation homomorphisms for field theory. Let f be a subfield of a field E, alpha be an element of E, and x be an indeterminate. The map phi alpha from f of x to E defined by phi alpha of a0 plus a1x plus etc. an x raised to n, which is equal to a0 plus a1 alpha plus etc. an alpha raised to n for a0 plus a1x plus etc. an x raised to n belongs to f of x is a homomorphism of f of x into E. Also, phi alpha of x equal to alpha and phi alpha maps f isomorphically by the identity map, that is phi alpha of A is equal to A for A belongs to f. The homomorphism phi alpha is called evaluation at alpha. Proof: the given lattice and mapping diagram may help us to visualize the situation. The dotted lines indicate an element of the set. The theorem is really an immediate consequence of our definitions of addition and multiplication in f of x. The map phi alpha is well defined, that is independent of our representation of f of x belongs to f of x as a finite sum a0 plus a1x plus etc. an x raised to n. Since such a finite sum representing f of x can be changed only by insertion or deletion of term 0 into xi, which does not affect the value of phi alpha of f of x. 1. If f of x equal to a0 plus a1x plus etc. an x raised to n, g of x equal to b0 plus b1x plus etc. bm x raised to m, and h of x equal to f of x plus g of x, which is equal to c0 plus c1x plus etc. cr x raised to r, then phi alpha of f of x plus g of x equal to phi alpha of h of x, which is equal to c0 plus c1 alpha plus etc. cr alpha raised to r, while phi alpha of f of x plus phi alpha of g of x equal to a0 plus a1 alpha plus etc. an alpha raised to n plus b0 plus b1 alpha plus etc. bm alpha raised to m. Since by definition of polynomial addition we have Ci is equal to ai plus bi, we see that phi alpha of f of x plus g of x equal to phi alpha of f of x plus phi alpha of g of x. 2. If f of x into g of x equal to d0 plus d1x plus etc. ds x raised to s, then phi alpha of f of x into g of x equal to d0 plus d1 alpha plus etc. ds alpha raised to s, while phi alpha of f of x into phi alpha of g of x equal to a0 plus a1 alpha plus etc. an alpha raised to n into b0 plus b1 alpha plus etc. bm alpha raised to m. Since by the definition of polynomial multiplication we have dj is equal to sigma I is equal to 0 to j ai b j minus I, we see that phi alpha of f of x into g of x equal to phi alpha of f of x into phi alpha of g of x. Thus phi alpha is a homomorphism. The definition of phi alpha applied to a constant polynomial a belongs to f of x, where a belongs to f gives phi alpha of a is equal to a. So phi alpha maps f isomorphically by the identity map. Again, by the definition of phi alpha we have phi alpha of x equal to phi alpha of 1 into x, which is equal to 1 into alpha, which is equal to alpha. Example 2. Let f be q the field of rational numbers and e be r the field of real numbers in the previous theorem, and consider the evaluation homomorphism phi naught from q of x to r. Here phi naught of a0 plus a1x plus etc. an x raised to n is equal to a0 plus a1 into 0 plus etc. an into 0 is raised to n, which is equal to a0. Thus by the given evaluation homomorphism every polynomial is mapped onto its constant term. Example 3. Let f be the field of rational numbers and a be the field of real numbers, and consider the evaluation homomorphism phi 2 from q of x to r. Here phi 2 of a naught plus a1x plus etc. a n x raised to n is equal to a naught plus a1 into 2 plus etc. a n into 2 raised to n. Note that phi 2 of x square plus x minus 6 is equal to 2 square plus 2 minus 6, which is equal to 0. Thus, x square plus x minus 6 is in kernel of phi 2, kernel of phi 2. Of course, x square plus x minus 6 equal to x minus 2 into x plus 3. And the reason that phi 2 of x square plus x minus 6 equal to 0 is that phi 2 of x minus 2 equal to 2 minus 2, which is equal to 0. Example 3. Let f be the field of rational numbers and E be the field of complex numbers, and consider the evaluation homomorphism phi I from q of x to c. Here phi I of a naught plus a1x plus etc. a n x raised to n is equal to a naught plus a1i plus etc. a n I raised to n, and phi I of x equal to I. Note that phi I of x square plus 1 equal to I square plus 1, which is equal to 0. So, x square plus 1 is in kernel of phi I. Example 5. Let f be the field of rational numbers and E be the field of real numbers, and consider the evaluation homomorphism phi p from q of x to r. Here phi p of a naught plus a1x plus etc. a n x raised to n equal to a naught plus a1 into pi plus etc. a n into pi raised to n. We note that a naught plus a1 into pi plus etc. a n pi raised to n is equal to 0 if and only if a I equal to 0 for I is equal to 0, 1 etc. n. Thus, the kernel of phi pi is the 0 space, and hence phi pi is a 1-to-1 map. This shows that all formal polynomials in pi with the rational coefficients form a ring isomorphic to q of x in a natural way with phi pi of x is equal to pi. 0 of a polynomial. Definition. 0 of a polynomial. Let f be a subfield of a field E and let alpha be an element of E. Let f of x equal to a naught plus a1x plus etc. a n x raised to n be in f of x, and let phi alpha from f of x to E be the evaluation homomorphism of theorem 3. Let f of alpha denote phi alpha of f of x, which is equal to a naught plus a1 alpha plus etc. a n alpha raised to n. If f alpha equal to 0, then alpha is a 0 of f of x. Theorem 4. The polynomial x square minus 2 belongs to q of x has no 0 in q. Proof. If alpha equal to m by n belongs to q is a 0 of f of x equal to x square minus 2, then phi alpha of f of x equal to f of alpha equal to 0, or alpha square minus 2 equal to 0, or alpha square equal to 2, or m by n whole square equal to 2. We now prove that there is no such a rational number m by n. If possible, suppose that m by n for m and n belongs to set is a rational number such that m by n whole square equal to 2. We assume that we have cancelled any factors common to m and n, so that the fraction m by n is in lowest terms with the GCD m n equal to 1. Now, m square is equal to 2n square, where both m square and 2n square are integers. Since m square and 2n square are the same integer, and since 2 is a factor of 2n square, we see that 2 must be one of the factors of m square. 2 is a factor of m square implies m square is an even integer, which implies that m is also even. For otherwise, m is odd implies m is equal to 2k plus 1 for some integer k implies m square is equal to 2k plus 1 whole square, which is equal to 4k square plus 4k plus 1, which is equal to 4 into k square plus k plus 1, which is also odd, contradicting the fact that m square is an even integer. Thus, m square must have 2 factors of 2, then 2n square must have 2 factors of 2, so n square must have 2 as a factor, and consequently n has 2 as a factor. We have deduced from m square is equal to 2n square that both m and n must be divisible by 2, contradicting the fact that the fraction m by n is in lowest terms. Thus, we have 2 not equal to m by n whole square for any m n belongs to set. Hence, the polynomial x square minus 2 belongs to q of x has no 0 in q. Let us summarize this session. In this session, we have discussed the rings of polynomials and have seen that under some conditions such rings are integral domains. We have observed that there is no field of polynomials. However, field of quotients can be formed from integral domain of polynomials. Expect you enjoyed this session. Now try to answer the following questions. See you next time. Till then, goodbye. How many polynomials of degree less than or equal to 3, including the 0 polynomial, are there in set 6? Question number 2. Consider the evaluation homomorphism 5 5 from q of x to r. List 2 elements in the kernel of phi 5. Question number 3. Give a polynomial of degree greater than 0 in set 7x, that is a unit. Question number 4. Prove that the least distributive law for R of x, where R is a ring and x is an indeterminate.